now we're getting into the very first devices. Now we're going to be talking about nozzles and diffusers. Now what a nozzle does is it creates a high velocity stream at the cost of pressure. So let's say we have steam, H2O in its gaseous form, in a pipe, and all of a sudden the pipe narrows gradually. So it ends up something like this. So it's going to be coming out much faster, so velocity is going to increase, but the pressure is going to decrease, the pressure of the fluid. And what a diffuser is, so this is a nozzle, a diffuser does the exact opposite. A diffuser starts off small and gets bigger. And it does the exact opposite. Velocity goes down, pressure goes up. So really, when working with them, they're interchangeable. They're pretty much the exact same. We do the exact same equations and work with both of them. The exact same assumptions can be made. So let's just write out the equation from last time. Q dot plus mass flow rate. This marker's not working. Mass flow rate. Enthalpy plus velocity in over 2 squared plus GZI equals W dot plus mass flow rate times enthalpy exiting plus velocity exiting squared over 2 plus GZE. So, assumptions we can make. First one really isn't an assumption, it's a fact. There's no work being done. There's no moving parts in either of these that can produce work. So nothing's being moved or anything, so there's no work. The next is that there's going to be very little heat transfer. There is going to be a very small amount of heat transfer from the fluid between the walls of the nozzle. However, this is usually very small, and only in cases of extreme temperature would we even take it into consideration. However, in some problems you may have to take into consideration a small heat transfer, but don't worry about it. The next one is that the change in potential energy really isn't that big either. Now again, there might be a problem where you have to take that into consideration, but not usually. And even then, changes in kinetic energy really aren't that small, even though we're going to be greatly changing the velocities. In the practice problem I'm going to be doing at the end of the video, we're going to take into consideration just to show you how small it really is, even when we really increase the velocity. Now, you'll notice that we have the same number on both sides of the equation, so we can cross that out, divide by m on both sides. So after all of our assumptions, we're left with enthalpy in plus velocity in squared over 2 equals enthalpy exiting plus velocity exiting squared over 2. And this is the equation that we're usually going to use when dealing with nozzles and diffusers. And time for the practice problem. In this problem, we're going to have steam enter into a nozzle, so it's going to and come out. So, and before it goes into the nozzle, its pressure is 600 kPa. Its temperature is 200 degrees Celsius. And it has a velocity of 50 meters per second. And when it comes out, all we know about it is that its velocity is 600 meters per second. And what we're going to do is we're going to find out what the enthalpy is at the exit. So we're going to start off by finding the enthalpy at the inlet state. This is pretty easy. We know it's steam, and we have pressure and temperature. So we're going to look at the superheated tables and look up under pressure of 600, temperature of 200, and we get the enthalpy to be 2,850 kilojoules per kilogram. So since I didn't say anything about the heat transfer between the steam and the walls of the nozzle, or any difference in height between the inlet and outlet, we can assume that those are negligible, that we do not have to take those into consideration. Which means we can use the exact equation that I derived earlier in the video of H1 plus V1 squared over 2 equals H2 plus V2 squared over 2. We're looking for H2, so we set the equation equal to H2. H2 equals H1 plus V1 squared over 2 minus V2 squared over 2. We know H1, we know this, we know that. We can find H2. So H2 is going to equal 2,850 kilojoules kilogram plus 50 squared divided by 2 times 1,000. Now the reason why we're dividing by an extra 1,000 is because the 50 is only in meters per second. So if we were to find out what energy it would have, all we would find out, the units it would be in would be joules per kilogram instead of kilojoules per kilogram, which is the units that we have enthalpy in right here. So what this is doing is converting into the same units that we have been using all along, which is kilojoules per kilogram. And we're going to do the same thing with the second velocity. When we do it all out, this becomes 1.25, see what I mean by little? And this becomes 180, which is less than negligible. We should take that into consideration, but really it's very small when we compare it to the initial 2,850. So we get H2 to equal 2,671 kilojoules per kilogram. Now, had I given you either the temperature or the pressure, you could then find out, we could find out much more about the outlet state. We could find out its specific volume and pretty much every other property that's in the tables. But since I only wanted to, this is a pretty easy problem just to get your feet wet, we only found enthalpy. And that's it for nozzles and diffusers.